Okay, this is video A2, and we're still studying exponential functions. If you remember last time, we dealt with in the lesson, which was f of x equals 2 to the x. And when we graphed it, we noticed there was an asymptote on this end, and then it grew, we would say, exponentially to the right. On your homework, I had you practice with one that was different. The base was 1/2. The multiplier was 1/2. And what you noticed is that the asymptote was on the right and it decreased exponentially. Okay, these are two completely different ideas here. This one we would call exponential growth. This one we would call exponential decay. So for our exponential function f of x equals b to the x, if b is greater than 1, as it is in our first example, this will give us exponential growth. Whereas if b is a value between 0 and 1, as it is in our second example, this is when we get exponential decay. And just as an aside, we're not going to deal with bases that are negative. Strange things can happen there. And we're not dealing with a base equal to 1, because think about that. If we had y equals 1 to the x, well, 1 to the 4th is 1. 1 to the 10th is 1. So that would just be a constant function and not an exponential function. So one thing we have to be able to do, I think this is example 2 now, is identify growth or decay. And they can be a little tricky. If I had f of x equals 1/2 times 3 to the x, okay, the 1/2 is a distraction. Okay, we'll learn what that is, but if you think about it, you already know what that is. That, since it's outside and it's multiplied, that must be some sort of vertical compression. But what we need to look at is the base of the exponential part, the multiplier right here. And since it's greater than 1, this would be exponential growth. So don't be distracted by the 1/2. Likewise on this, if I have g of x equals 7 to the 0.1 to the x, okay, the 7 is the distractor. This is the important part, the base. Since it's between 0 and 1, we would have exponential decay. And then finally, if I have h of x equals 4 times x to the 1/2, and this is the trickiest one, this is in no way an exponential function. Remember, with exponential functions, the variable is the exponent. Here, the variable is the base. This is actually 4 times the square root of x. Because remember, 1/2 exponent means square root. And so this is neither. It's just a vertically stretched square root function, like we've studied. Okay. And an important thing I want you to really focus on, and this problem right here brings that up, is the difference between a linear growth function and an exponential growth function. A linear function might look like this. You know how we have y equals mx plus b, slope-intercept form? Okay, so if I have j of x equals 3x plus 1. Okay, there's my slope, and there's my y-intercept. So remember, y-intercept is always our starting amount. Your slope is always some sort of rate. And so our rate of growth is, if you think about this, is 3 over 1. And rise over run, every time we go 1 to the right, we go 3 up. Okay, and if we make a really quick table of values, I'm going to start I'll put x is 0 in here, and then j of x. Okay, if x is 0, I start at 0, 1, the y-intercept. If I then go to 1, I get 3 plus 1, or 4. Notice that we grew by 3. If I go to 2, x equals 2, I get 6 plus 1, or 7. Once again, we grew by 3. And so with a linear function, you're changing by a certain amount every time. But that isn't what's happening at all with an exponential function. So an exponential example, an exponential function, might be something like, remember this is going to be the y equals b to the x. Let's say I have k of x equals 1.3 to the x. You notice that my multiplier is bigger than 1, so this will be exponential growth. And so let's go ahead and see what we're doing here. And then we'll talk about how to break that apart to understand really what we're doing. So I'm going to start with x equals 0, and I'll get my k values. So if x equals 0, 1.3 to the 0 power is 1. And so we talked about that earlier, that 0, 1 must be some sort of important point. It looks like another y-intercept there. Okay, but when I go to 1, 1.3 to the first power is 1.3. If I then go to 2, so we increase by 0.3 here, right? So if I go to 2, I'm going to now use my graphing calculator. I hope you can see this. So if I have 1.3 squared to the second power, I get 1.69. Notice that we didn't increase by 0.3. What we actually did is we increased each time by 30%. And if you break this down, you can clearly see why it's 30%. 1.3 is equal to 1 plus 0.3. And in decimal form, or I should say this, these are the decimal forms of the percentages: 100% plus 30%. So 1 is 100%, 0.3. Remember, percent means divide by 100. If I were to divide 30 by 100, I'd get 0.3. Okay, and so breaking down the multiplier, you can see not only that it's exponential growth or decay, you can see by how much you're growing or decaying, by what percentage each time. Okay, and so that brings up the exponential growth or decay model. And since we're using the word model, I'm probably going to get some word problems with this. And it looks like this: a of t equals little a, 1 plus or minus r to the t. And so this kind of looks like this, except we have something out here and the multiplier is broken down into the 100% plus or minus some sort of rate of increase or decrease. So let's look at each part of this. Okay. We'll understand why in a little bit, but this a right here is your starting amount. This 1 right here represents 100%. The r is your rate of change. The t is the number of times you apply the change. And then your a of t, this will represent the amount after t changes. Okay, and so I'm going to maybe leave this, no, I'll rewrite it on the next page. And so our exponential growth or decay model, a of t equals a, 1 plus or minus r to the t, allows us to answer questions like this. So this is question 3 in this section now. Let's say we have 20 people are in infected by a virus. If the number of people infected increases by 8% each day, how many will be infected after 60 days? Okay, and so if A represents our starting amount at t equals 0, okay, A must be 20, so I'll label that as little a. 8%, we're increasing, that's an important word there, we're increasing by 8%, so this must be our rate of increase. Okay, we're increasing each day, and there are 60 days, and so this must be the number of times we're going to apply this multiplier here. Okay, and so the amount infected after 60 days will be the initial amount, 20, and then 100%, in this case it's plus because we're increasing, so we're adding 8% each day. And to represent 8% in decimal form, it's 0.08. Remember, you're dividing 8 by 100%. Okay, and then our number of times is 60. Now it's time for the calculator. We're not going to do that in our head, so just type it in carefully. We have 20 times, and I'll just add that in my head here, 1.08, and then caret 60, hit enter, and we see that we have 2,025.14 people infected. So 2025.14. Okay, now we don't want 0.14 people, okay, and so maybe this last person isn't quite infected yet, so we'll round to 2,025 people after 60 days, just starting with 20. And another example would be something like this. Number 4, a city population was 15,500. The population decreased by 3% per year for 20 years. How many people are left? Okay, so let's identify the different parts of our exponential growth or decay model. Okay, the initial population was that, so that must be our A, our starting amount. Okay, the population decreased by 3% per year. Decrease is a key word here now. And 3% must be our rate. And then it's 3% per year. There are 20 years, so T must be 20. Okay, so let's write it out. We're looking for the amount of people left after 20 years when we have an initial population of 15,500. Okay, we had 100%, but now we're subtracting because we're decreasing. We're subtracting 3% per year. So remember, you're dividing 3 by 100. And we're applying this multiplier 20 times. So once again, this is going to be a calculator problem. Hope you can see that. So I have 15,500. We can do this in our head, or you could use your calculator to do it. Here, I'll use the calculator. But we're going to get, basically, isn't that 97%? So what that means is each year, you'll have 97% of the population that you had the previous year. Okay, and then we're going to raise that, so I hit the caret button again, to the 20th power. So we have 8,428.81 people remaining. Okay, and so maybe that last person didn't leave yet, and so we'll round to 8,429 people. Okay, the homework problems that I want you to try are these. I'll let you look at that for a little bit, but now I'd like for you to pause the video. I'm about to flip this over and show you the worked out solutions. Good luck.